My name is Guido Müller. My main job these days is I'm the director in the Max Planck Institute for Gravitational Physics in Hanover, in Germany. I'm also professor at the University of Florida, in Florida, obviously, and will soon be also professor at the Leibniz University in Hanover, which is a whole lot of titles which are completely meaningless and are just part of the job.
And why did you choose a career in physics?
By accident, I ended up in physics. I was fairly good in physics in school, obviously, kind of. We were in a crisis in Germany at that time, so I couldn't find a real job. Ended up in the military, and then I ran into a person who wanted to study chemistry, and I said, okay, then I start studying physics. My parents panicked because they did not know what that actually means, but I stuck with it, and now I'm in the position I am in. By accident, essentially, is a fair answer.
And what's the best part of your job?
I think the best part of the job is actually that you work a lot with young people, with students, to be honest. That keeps you young, that keeps you alert. You have scientific discussions with many people, certainly also senior people, but also often with junior people, with students, with postdocs. And I think interacting with young people is a real blessing for us.
Can I ask you to give an advice to young people? What advice?
Advice for young people, I think, especially in physics, people should not worry too much about paper counting and things like this. They just should do their job, should do their work, should do what they love to do and be good at it. And don't worry too much about paper counting and things like this, but just get your job done and do what you want to do. Follow your own goals. Yeah.
So what's the topic of your research, and how would you explain it to a kid?
So I grew up, essentially, scientifically, I grew up in the gravitational wave community, which started to build serious detectors in the 1990s, which was when I was still young in the career. So gravitational waves are strange things. They just stretch and squeeze space-time. They change distances by very minuscule amounts. And they're generated by highly accelerated masses. It essentially means by these fantastic black holes crashing into each other with the speed of light. And if you're not interested and excited by black holes that are crashing into each other with the speed of light, you shouldn't be in physics and astronomy. So it's really an interesting part, most interesting, most energetic events in the universe, in my opinion. And trying to detect them, trying to measure them is what actually keeps me awake at night. And this is what I'm trying to do, try to build detectors. I was already heavily involved in advanced LIGO. We did the first detection, and now we're trying to build a space mission to detect gravitational waves from even heavier objects at lower frequencies. This is what keeps me going at night, trying to build a detector that can detect things people have thought would be undetectable, including Einstein, who actually discovered gravitational waves theoretically.
Okay, and how would you explain it instead to a student of the physics bachelor? So what kind of information you can add?
Oh, pretty similar, right? We're measuring space-time changes generated by gravitational waves. The space distortions are things we can calculate these days, fairly straightforward way. Reaching now the sensitivities we need, trying to measure picometers over gigameter scales. Relative length changes in the order of 10 to the minus 20, 10 to the minus 23, 10 to the minus 25 these days with advanced LIGO is just amazing to me. In some way, you're thinking about the largest things in the universe, and you're trying to measure the smallest changes. And this difference in scales is something that should keep physicists excited.
Okay, and one last question. Can you explain, to a broad audience, how LISA is going to work?
How is LISA going to work? So we have essentially inside the spacecraft metal cubes which are just freely falling, so that they are isolated from all external forces, and they're freely falling around the sun. And now we're trying to measure distance changes between these cubes with laser interferometers. So we send laser beams back and forth between these cubes, and we look at minuscule changes in the phase of the laser phase at the order of 10 to the minus 6 of wavelengths, so 10 to the minus 12 meters. It's like a little bit of noise in your radio signal that you won't be able to hear because it's way too small. But this is kind of what we're trying to measure.
If you enjoyed the video, like and subscribe.